All right, 14.6. Spherical coordinates. So, for an intro into this, the entry point into this is to notice that very often rectangular and cylindrical coordinates aren't ideal for some simple objects. So rectangular and cylindrical are less than ideal for some simple objects. So I'll give you an example. So like something like a sphere, right? Really, really simple thing, centered at the origin. This guy, we put an axis there. In a rectangular is x squared plus y squared plus z squared equals, let's say the radius is 3. So that's equal to 9. In cylindrical, this is r squared plus z squared is 9. Neither of these is ideal. Like they have a z in them. Spheres are round. In some sense, they have no reasonable sense of x's and y's and z's. So neither feels natural. I'll put natural in quotes because this is not a rigid term. Neither feels natural for a sphere. So question, is there another way? So the answer is actually there are many, many different ways, but yes, there's one particular nice one. So spherical coordinates will do the job. So what we'll do is we'll approach this in a few steps. We will first talk about how spherical coordinates work. And then we'll talk about some conversions. Then we'll talk about how to describe some objects in spherical. And then we'll talk about the ramifications this has on integration. So to spherical coordinates. So here's how it works. Every single point in space is determined by 3 points, just like before, but they're different now. So the points that we use, or points is a bad word, sorry, 3 values / numbers. So what those are is the following. We have theta. This is the theta that you know and love. This is the angle with the positive x-axis. Then we have this guy, phi. This is the angle with the positive z-axis. This may seem a bit weird, that's okay. These two together give a sense of direction. These give a direction from the origin. We'll see this in a second in a picture. And then we have this guy, rho, which is distance from origin. So here's a picture that captures all of these. So what we'll do is, I'm going to sort of draw this picture in a very special way. So I'll draw the x and z axis first. And then what I want you to imagine is there's a door. And the door is hanging from the z-axis, like that's the place it swivels. So that's our door. Let's finish the y-axis. Is the y-axis hiding behind here? Then I'm going to fill a couple things in. So theta is this angle right here, the bottom, from the positive x-axis. Here is the point of interest up here in the upper right. Phi is the angle in here, from the positive z-axis. And then rho is this distance in here. So a couple things to note here. I'll put them down the edge here. Is that phi equals 0 is up, straight up. Phi equals pi is straight down. Phi equals pi over 2 is the xy plane. Keeping these in mind can help figure out the whole phi. And then the other thing to consider is that rho is always greater than or equal to 0, its distance, and rho equals 0 at the origin. So we won't do a lot of plotting of points, but let's just plot one specific point just so we can get a grip on what's going on here. So let's plot just one single simple point. So we'll plot theta would be 3 pi over 4. Phi will be pi over 6. And rho will be 2. Just to get a sense of where that would be. So if we go into three-dimensional space, try and draw this as nice as possible. So theta, 3 pi over 4, that takes us around here to right there. So then what you want to imagine is you're at the z-axis, positive z-axis, and you drop down towards that line by pi over 6. So if you continued there, you would end up towards that angle. You're sort of above that. And then the point that you're at is 2 units out. So there is our phi, there's our theta, and that's our rho in there. And this is the result. So I haven't drawn this to any kind of scale or anything like that. We're not going to be doing a lot of plotting of points, but that's at least one, so we can get a sense of where things are. So the deal here is that we won't plot a lot of points. Really won't plot any. But what we do need to do is we need to know how to convert objects. Like we need to describe objects. So to do that, we need to know about some changes of variables. So we need to know basically how to convert x and y and z into spherical. So to do this, what I'm going to do is I'm going to redraw the door picture, the picture that's on the right. I'm going to draw it a bit bigger, and so I can add more information. So here's the picture again, with more detail, or really with more data on it. So here's the picture. I'll have lots of space around it. There's X, there's Z. Then we draw the door again. So here's the door. Here's the y-axis over on the right. And so what I'm going to do is I'm going to label a whole bunch of things here. Right, so first of all, we still have this line going up here. We have our point. We have our theta in here. We have our phi in here. We have our rho, right? So I'm also going to label a few other things. So I'm going to put in the r from polar coordinates. That's right here. It takes us out to this point right here. I'm going to draw a dashed line here. And then this distance over here is x. I'm going to draw a dashed line here. This distance over on the right is also x. This dashed line distance is y. Up here at the top of the door, this is also r. This is a right angle right here. To the right of the door we have z, and over on the left we also have z. Same thing. right? So take a second, digest that picture, see if that makes sense, and then what we'll do is we'll make some observations that stem from that. Right. So observe. A few things that come out of this, right? So first of all, take a look at the angle phi. Right, so that's a right triangle over here. It's right here. Take a look at that triangle. We're going to use that triangle twice. Right, so in that triangle, if we look at the cosine of phi, cosine is adjacent over hypotenuse, so that's z over rho. So what that tells us is that z is rho cosine phi. That's the first thing. We've got z in terms of the others, in terms of the spherical coordinates. Right? Now, in addition to that, we have sine of phi is r over rho. Now, r we don't really want, it's just in there to sort of help us out, but it does tell us that r is rho sine phi. Right? Now, this may not seem useful, except we know from polar that x is r cosine theta. So this tells us that x is rho sine phi cosine theta. That's the second fact. And similarly, we know that y is r sine theta. So this tells us that y is rho sine phi sine theta. So these are our basic conversion things. This is z up here. This is x. This is y. Right? Now there are two other things that we can write down that are useful. So in addition, we have rho, which is the distance to the point. Using the Pythagorean theorem, we have rho squared equals x squared plus y squared plus z squared. So this is useful in its own right. And then in addition to that, from polar, we know r squared is x squared plus y squared. And we know that r itself from back up here on the right is rho sine phi. So rho squared sine squared phi is x squared plus y squared, also useful. So these 5 things will be helpful when we convert objects from rectangular into spherical. So we'll do that next. Look at a few basic objects. So take a look at all this. I'm going to clear the screen, keep these 5 things in mind, and then we'll convert some objects. So we'll say objects in spherical. And we'll do this by looking at a few examples. So first one, spheres centered at the origin. These are really nice. For example, the sphere x squared plus y squared plus z squared equals 9. This just becomes rho squared equals 9, or rho equals 3. Now this kind of makes sense because what we're saying is the distance is 3 from the center, and we can have any direction we want. All right, so this makes sense. All right, distance from origin is 3, any direction. So second example. Let's actually, let me just draw a really quick picture up here. So this is the standard sphere that we know and love right here. Radius 3, right there. Now, second one. Look at something like a cone. Okay. So cones in spherical are actually really nice. So consider the following equation. Phi equals pi over 6. What does that mean? That means the angle with the positive z-axis is pi over 6. Oh, yep, positive z-axis is pi over 6. Then we have any theta, any distance. So the result of this is exactly as you might expect. We get a cone right here. The pi over 6 is this angle right here. So it's a really, really nice and simple equation in spherical coordinates. So let me do two more. Next one's also nice. Well, next one's less nice, but it's okay. What if we had the cylinder x squared plus y squared equals, say, 4? Right? Well, we know that x squared plus y squared is rho squared sine squared phi. So this tells us we get rho squared sine squared phi equals 4, or rho sine phi equals 2. Right? Now, in addition, it's worth noting that very often when we're working with sphericals, we'll want to solve for rho. Right? So this can also be written as rho equals 2 cosecant phi, or 2 over sine. So this, I want to do this one because it's sort of a bit peculiar. It's not obvious when you look at it, it's a cylinder, but it is. Right? And then last but not least, planes aren't particularly nice. So the plane z equals 2, this becomes, we know that z is rho cosine phi. So if we solve for rho in this one, we get 2 secant phi. Again, not so nice for a plane, but that's what it is in spherical. Not so nice at all. So these are some basic objects. We'll have a few more as we go, but these are sort of like some good fundamental ones to keep in mind. So what we need to do next is talk about describing like solids, right? These are all sort of hollow objects, hollow spheres, hollow cones, planes, things like that. What about a solid object, like a solid D that we might integrate over? So let's take a look. So for solids in spherical. So what I'll do is I'll give you a brief intro, and then I'll just give some examples, because the intro and the examples will make it clearer than trying to give some general explanation. So the basic idea is to give the following. So A, a range of thetas. B, a range of phis. And C, I'm going to say a range of rho, but these are very special. This is from the point of view of the origin. This is like a near function and a far function. A near, let's say a near rho and a far rho. So this may seem a bit confusing at first, and that's perfectly fine. So let's charge through a few examples and see what's going on. Right? So let's go back to a sphere, and what I'm going to look at here is a solid sphere. So it's like a solid ball, really. So we'll center at the origin. We'll imagine that it has, say, radius 3. Perfectly good. So hopefully you can visualize this as solid. So what I want you to do is put yourself at the origin. So you're right here in the middle. And ask yourself these three things, theta, phi, and rho. Like, what do these need to be to describe the sphere, right? So what we see here is as follows. That theta, if you're at the origin and you look around theta, theta goes around in the xy plane, angle with the positive x-axis, we see that theta ranges from 0 to 2 pi, all the way around. Phi is a little different. Remember, that goes from the positive z-axis, so that goes straight up to straight down. So that ranges from 0 to pi. And then rho, well, if you're at the origin, there is stuff right there at u. So rho ranges from 0 to a radius of 3. That was our radius right here. So these values, these ranges, determine the entire of the sphere. You can think of it like a parameterization of the sphere, of the solid sphere. Again, keeping in mind it's filled in. That's what the range of rho says. So what we'll do now is I'm going to start hacking pieces off this sphere and seeing how these values change. So suppose we took just the top half, just the hemisphere. So again, it's solid. It's a solid hemisphere. Still radius 3, not going to change the radius. So the only thing that changes here is that the phis change, because in this case theta still goes all the way around in the xy direction, 0 to 2 pi. Phi now goes from straight up, which is 0, to the xy plane, which is pi over 2. And rho still goes 0 to 3. So again, these three things, these three ranges dictate the entire solid hemisphere. Right? Now, I'm going to gouge out the hemisphere one more time. Well, two more times actually. So what I'm going to do first is I'm going to keep only a quarter of what's there. So I'm going to keep the quarter that's sort of in the back. So what we have here, try and draw this as nice as possible. Is the piece that's sort of in the back quadrant, or back octant right there. So for this one now theta changes because theta doesn't begin until pi over 2. So theta goes 0, oh sorry, theta goes pi over 2 to pi. Phi still goes 0 to pi over 2, and rho still goes 0 to 3. So just in case it's a little unclear, the theta is very often the trickiest of these. So the thing to keep in mind is theta begins right there. This is pi over 2. As you swing around, there is nothing until you get to pi over 2, and it continues all the way around to the back, which is at pi. So that's why we have that. Okay. So I'm going to do one last thing now. I'm going to gouge out a piece of the sphere. So like gut it a little bit, right? So we get here, I'll try and draw a delicate drawing here, is something like the following. So something like that. I won't make it too, I won't add too many things to it. Try and just do enough that we can see what's going on. So I gouged out a little piece of the sphere in the middle. So let's say it's still radius 3 on the outside. Let's say it's 1 on the inside. So it's just like, it's like a piece of cantaloupe or melon or something. So now in this case, we have theta goes pi over 2 to pi. We have phi goes 0 to pi over 2. And we have rho goes from 1 to 3. So now the rho changed in this one. So a little note here before we proceed is that in all of these cases, all of these values are constant. This won't always be true, but it will be true for the theta and the phi. So these two guys always constant ranges. For rho, perhaps not. So we'll see an example in a minute, but last thing we need to do is sort of say like, okay, what does this say about about integrals. Actually, before that, let me do one more. I'll do one more solid where one of these things, one of these rows is not a constant, just so we can see. And then we can dive into integration and see what's going on there. So I'll do one more example. It'll certainly be slightly more confusing than the others, but hopefully it'll be clear. It'll really help see what's going on. So what I'm going to do is I'm going to do a cone. The cone I'm going to do will be flat on top. So the top is going to be the plane z equals, say, 3. And the sides will be phi equals pi over 6. So give this some axes. X-axis, y-axis, z-axis. Right? So this is solid. So think about what's happening here, right? So we still have theta goes 0 to 2 pi all the way around, right? We still have phi goes from straight up, which is 0, to where the cone ends. So if you imagine your angle phi dropping down, that stops at pi over 6. There's no more cone beyond that. And then rho is the tricky one, right? So put yourself at the origin, and if you head out into the cone, there's cone immediately, so it goes from 0, and then it goes to the plane. Now the plane is z equals 3. And z equals 3, this is rho cosine phi equals 3. So this is rho equals 3 secant phi. So if it's a bit confusing, here's an additional picture that just may help see that. Let me draw the cone without any extra stuff. So put yourself right here, right at the origin. And then we're going to draw a line. Right? So draw a line up through the cone. It pops out right here. So this is the outer row. The inner row is just the center. So the outer row here is the plane. So that's the way you want to think about these. It's sort of like a three-dimensional version of polar coordinates, but not quite. So in this particular example, this is the data. So we have all these, and then this guy right here, 3 secant theta, that's what goes right there, 0 to 3 secant theta. Oh, sorry, 3 secant phi. So again, 6 parameters, 6 values, 3 pairs if you like, and these are all going to feed nicely into the integral. So then the big question is, okay, how does this work with an integral? So what I'll do is I will talk about how to do this, and then I'll do this one single example, and then I'm going to put a few more examples in a separate file to keep them separate and to keep this file fairly short. So integration. So here's the deal, and I want to keep this example on the left in mind. So if D is described in spherical, then this is what we get. The triple integral over D of f of xyz dv. So this is what happens. So the outside integral, this is the range. This is the range of thetas. So I'm going to say alpha and beta, and I'm going to label those in a second. Next one is the range of phis. So I'm going to say gamma and let's say delta and gamma. The next ones are the range of rows. So we'll say near row and far row. Then we have our f, but we have to replace x and y and z according to spherical. So we'll have rho sine phi cosine theta. We have rho sine phi sine theta. And then we have rho cosine phi. Then, because we're changing to a new coordinate system, we have like the polar r that comes up, but we have the spherical version. So that's rho squared sine phi, and then d rho d phi d theta. Right? So let me just clarify a few things here. This first one, this is the theta range. Second one, this is the phi range. Third one, this is the rho range. This thing over here, this is the Jacobian. This is the don't forget me. In 14.8, we'll understand exactly why this is happening. And then all this stuff in here is just saying replace x, y, z by spherical. So, and we just end with a really, really simple example. So for example, if D is this guy over here, this cone, then suppose we were integrating, say, x dv. All that would happen is I would dump all those values in. So 0 to 2 pi, 0 to pi over 6, 0 to 3 secant phi. Then we have an x. X becomes rho sine phi cosine theta. Right, that is x. Then we have the Jacobian, which is rho squared sine phi. And then we have d rho d phi d theta. Right? And then that just gets evaluated. It doesn't mean it's easy, right? This one is not so easy necessarily, but that's what we do from here. So I'm going to do a few more of these, but I'm going to do them in a separate file, but I just wanted to end on this. So we have side by side the method down on the left, or down on the right, and then an example that feeds in from the left. So look for the addendum to do a few more examples of this.